Uh, Hello, everyone. I suppose that you can hear me. I see that we are in 18 present here on this meeting, on this call. I'm going to share my presentation. Excuse me. Okay. Share the screen, show Windows. Yes, it should be the right one. Can anyone confirm that you can see my screen?
Yes, Daniel, we see your screen.
Okay. Okay. Not the right one. Yes, that's it. So once again, hello everyone. We are going to resume from where yesterday we left. So that was my last slide. I will resume from this one. So yesterday I talked about GNSS positioning methods taxonomy, and it was stressed that there are some combinations that could be used in assessment of the earthquake effect. If we are talking about absolute positioning, there is a PPP method which provides feasible and satisfactory results. And on the other side, there is a relative positioning providing the best quality results for geodetic, for example, for geodetic purposes, only if phase observations in addition to code observations are used, and there are feasible two solutions: static observations, which provide the best quality solutions, and of course there are also available kinematic observations, both static and kinematic in post processing. So those methods marked in orange color and those marked in red color are usable, are feasible for the assessment of earthquake effects. So let's go to see what is the PPP, the precise point positioning. It is an absolute positioning technique, as you saw in the previous slide. It is an absolute positioning technique that removes or models GNSS system errors to provide a high level of positioning accuracy from a single receiver. So a single receiver is all that is so the data are collected on the field using only a single receiver. So there is a comparison between the standard positioning service, which is used, for example, which we use every day with our mobile phones, having featuring a GNSS chipset. So what we have in standard positioning service. So there is a broadcast orbit and clock information in addition to the user satellite tracking information provided by our receiver. And together, what we get, we usually normally get meta level user position estimates. But for the assessment of earthquake effects, this is not enough. We need more precision. And here comes the PPP. So what is inside the PPP method? So instead of broadcast orbit and clock information, we use the precise orbit and clock information I showed you related to IGS as a global service, the accuracy with which the orbit and clock information are provided. In addition, we need the user satellite tracking information. This, as you can see, this is the same as we have in a standard positioning service. Then we need some additional error modeling This is needed in order to assess or model the errors. This is why I showed you those slides related to error sources, and together, so with precise orbit and clock information, with the user satellite tracking information and additional error modeling, so combined, we can get decimeter to centimeter level user position estimates. Centimeter level is much more better than meter level, and it could be used for assessment of earthquake effects. So basically, how does the PPP work? So as you can see on the figure, in relative or differential positioning methods, we have at least two receivers simultaneously observing the same satellites. We have here, of course, the minimum number, which is 4 satellites observed by both receivers. On the other side, we have the PPP, which is an absolute method. We have only one receiver observing at least 4 satellites, but we have also some additional information in order to assess the errors and to improve the accuracy, to improve the performance. Namely, you can see there is a logo of IGS providing those additional information, for example. But you can see above these 4 GNSS satellites, there is a communication satellite providing those data. That means that the additional data can be provided via satellite, or it can be provided via internet. So basically, PPP as method uses state space representation, correction products such as precise satellite orbits, clocks, and signal biases from either commercial and public services. For example, there is stated IGS that are delivered to the user via satellite and or internet. So basically, this is how the PPP method works. So, of course, there is no perfect method. Each method has its advantages and, of course, its disadvantages. The advantage of PPP is that it provides a positioning solution in a dynamic global reference frame, such as, for example, International Reference Frame or ITRF. So directly, you do not need a reference station. By directly, you obtain your solution in ITRF. What is a disadvantage? So the most significant disadvantage being the long convergence times of the order of 20 minutes or more necessary for the ambiguity flow solution to converge as to ensure centimeter level positioning accuracy. Why longer time is needed to achieve that level of accuracy? Just bear in mind that you have only one receiver, and that one receiver have to cope with all those error sources. So it needs a lot of time, it needs a lot of information in order to model the error and to converge from the float ambiguity level to a fixed ambiguity level, since the phase observations are needed to obtain the centimeter level position accuracy. So PPP requires a number of corrections, I said before, to be applied to account for centimeter level variations in undifferenced pseudo range and carrier phase observation biases. So in relative or differential positioning, we have differenced observations. In PPP, they are used undifferenced. And this is why a longer time is needed, much more data is needed, additional data are needed in order to achieve centimeter level precision. So this is a table showing the error sources, and there is a comparison between the PPP as an absolute method and differential GNSS differential GNSS method. So in PPP we use single receiver. In differential we use at least two, or relative method. So the rules applies to both. In differential we have at least two receivers, one being base receiver and the other one being the rover receiver. So we have satellite specific errors, we have receiver specific errors, we have some geophysical models, and we have, of course, atmospheric modeling. So the precise satellite clock correction is needed for the PPP. For differential, it is not so critical. What is applied in both methods are the satellite antenna phase center offset and satellite antenna phase center variations. Precise satellite orbits are needed for PPP. In differential, they are not needed. So if we are talking about droop delay differential, in differential GNSS, it is not needed, but it has to be taken into account in the PPP only if the receiver is a single frequency. Two additional error sources which have to be taken into account for PPP are the relativity term and the satellite antenna phase wind-up error. When we are talking about receiver-specific errors, so namely the phase center offset and phase variation, in addition to the phase wind-up, all those have to be taken into account for the PPP. Geophysical models, all four, so the solid earth tide displacements, ocean loading, polar tides, and plate tectonic motions, all those sources have to be taken into account. If you just compare the situation with the differential GNSS, all those error sources are not needed, since the effects simply cancel out in process of process of differentiation. There's also atmospheric modeling, so tropospheric delay have to be taken into account. Ionospheric delay in differential GNSS can be cancelled out, especially for the short baselines. In the PPP, it has to be taken into account. So just to keep it short, biases and errors that need to be applied or accounted for in a typical PPP are shown in this table. So how we can obtain coordinates by PPP? There are basically two ways. One way are the online services. The other way are the applications, being standalone or network applications. There are some some examples. For example, there is a Canadian Spatial Reference System Precise Point Positioning Service. There is a Magic GNSS. There is a APPS. There is a GAPS Positioning Service. And there is also a service that will be explained in much more details and will be used or has been used in the case study. And of course, there is an example of application providing PPP solution, and it is GLab. There's RTK-lib and so, a number of different applications providing PPP solution. In the table in the lower right corner of your screen, there is a comparison between different online services. You can see that they provide the static processing and kinematic processing solutions. And there are, of course, there are some differences in way the processing is performed, being the solutions smoothed, or there is the solution is provided by a batch processing. So I'm going directly to dive into a PPP online service provided by Trimble company. So the service is called Trimble Center Point RTX post processing. You can see on the figure, this is the screenshot from so this is the initial window of that service. So it basically uses a Trimble RTX technology to post-process user-submitted GNSS observation files, providing high accuracy coordinates for anyone nearly anywhere in the world. So basically, as you can see, you have to be registered in order to be able to use the service. And basically, it is stated that the service provides better than 2 centimeter horizontal accuracy, GNSS compatibility, and no base station is required. So those are the features of post-processed PPP method. So this is a list of main commercial augmentation services. The list is provided in the GNSS User Technology report released by the former GSA, European GSA, which in the meantime was transformed to the USPA. And you can see there is a number of providers, and mostly the solutions are provided by the PPP method. But if we just zoom into the solution provided by Trimble company, we can see that there are 4 services providing different level of accuracy. The best one being the center point, which will be shown in much detail, provides accuracy better than 2 centimeters. It supports all global navigation satellite system plus QZSS, the Japanese one. This is the system that was not addressed yesterday, since QZSS is not real global system. It's much more regional one applied to the Asia Pacific region. And the delivery method is by internet or by L-band, emitted from the usually geostationary satellites. But all those 4 services provide the solution using PPP method. So Trimble RTX is an acronym of real-time extended, is a high accuracy global GNSS correction technology that combines real-time data with positioning and compression algorithms to provide centimeter level positioning accuracy. It utilizes real-time data from a Trimble-owned global reference station infrastructure. So it does not use data from IGS, or primarily uses from a Trimble-owned global reference station infrastructure to compute and relay satellite orbit, satellite clock, and other system adjustments to the receiver. So what are the other system adjustments? You have seen that in on one of the previous slides, where the sources of errors are explained to the very detail. So these adjustments are transmitted to the receiver via satellite, via internet protocol, being IP or cellular, while post-process results are sent to the user via email or a client interface. Indeed, the data that I'll show you, or result that I'll show you later on in the use case, were sent to the user via email. So the Centerpoint RTX post-processing service is free and is available for all users. Of course, users are required to register every year to get unlimited use to the service. So it's free, but you have to register before the first usage. So what are the features of Trimble Centerpoint RTX? So one of the features is related to accuracy. The achievable accuracy level of the Centerpoint RTX post-processing is 2 centimeters or even better in the horizontal and approximately 6 centimeters in the vertical. As I showed you yesterday, so the heights are determined 1.5 to 2 times worse than the position. This is why we have here this ratio 2 to 6. This accuracy is based on a minimum of 1 hour of observation file. As the data session approaches, but does not exceed 24 hours, accuracy can approach 1 centimeter in the horizontal and 3 centimeters in the vertical. So basically, you cannot use observation file shorter than one hour because they do not guarantee the estimated accuracy level, since time is needed to obtain the convergence and to obtain a fixed ambiguity solution. The Centerpoint RTX post-processing service supports any brand or model of dual frequency receivers. So since it is a service provided by Trimble, it supports all receiver brands, but there is one request that the receiver must be at least dual frequency, or better if it is a multi-frequency receiver. Specific antenna types are supported by Trimble RTX post-processing service, and they are listed on this link. On the bottom of your screen, there is just a small screenshot of the antenna types supported. And the antenna type that I used for the use case is this one. So it is supported by Centerpoint RTX. What are the requirements for the observation file? So in addition to the minimum time frame being 1 hour, there are some additional requirements. So basically, the observation files must meet the following requirements. Data formats accepted include Trimble proprietary data, and the system or the service accepts the standard RINEX 2 and RINEX 3 data formats. For optimal processing results, it is recommended to provide at least 60 minutes of observations. It means, as I said before, at least 1 hour of observations. But data cannot exceed 24 hours in length. Data files must be static, so kinematic files are not supported. Data files must contain dual frequency pseudo range and the carrier phase observations, and at L1 and L2. Data must have been collected after the May 14, 2011. BeiDou data is included since the June of 2014, and Galileo was included later on, namely from 1st of January 2017. And if your observation data consists of several files related to the same point, to the same location, you can compress all those files in a zip archive and upload it as a single file. Of course, all those files in the zip archive must belong to the same station. So, as you have seen, the achievable accuracy is very closely correlated to the length of the observation file. It is recommended to use data sets that are a minimum of 1 hour in length to achieve 2 centimeter horizontal accuracy. Data sets less than 1 hour will result in a less accurate position results, or even they are not accepted. Data sets longer than 1 hour will yield even greater accuracy and can approach 1 centimeters. The center point RTX post-processing service does not accept observation files that are longer than 24 hours, as we saw before. What about a logging rate? So the recommended observation rate is 10 seconds. Files with higher observation rates, namely 1 second, 2 seconds, 5 seconds, will be accepted, but the service will decimate to 10 seconds before processing. And files must have an observation rate higher than or equal to 60 seconds. So if you provide your data, let's say in 2 minutes logging rate, the files will not be accepted, since those logging rates do not guarantee the achievable accuracy. Data sets that were collected prior to March 23rd, 2017 are derived in the observation epoch, the current epoch of the RTRF 2008. And if data sets were collected after that date, so solutions are derived in the observation epoch, meaning the current epoch of the most recent RTRF 2014. The center point RTX corrected post-process positions can be transformed to a number of reference frames. This is a not exhaustive list. Of course, at the top of this list, we have RTRF, excuse me. Okay, so we have RTRF 2014 and 2008 at the current epoch, but also at the reference epoch 2010.0 for the RTRF 2014 and the reference epoch 2005.0 for the RTRF 28. Of course, there is a number of other reference frames, which is what is interesting for us in Europe. It is the RTRS 89 at epoch 1989.0 and ETRF 2000 release 05 at the reference epoch 2000.0. So the center point RTX post-processing service allows the transformation of the current epoch of the ITRF 2008 or ITRF 2014 position to another reference frame with a different reference epoch and based on a selected tectonic plate. So that the transforming of positions is computed at the observation epoch to a fixed epoch requires knowledge of the station velocity due to tectonic plate motion. If the velocity is not available, it must be determined from a tectonic plate model, such as Morrell's 56, which is implemented in ATX. So in June 2014, the tectonic plate model was changed from Nouvelle 1A to a Morrell 56, and the following tectonic plates are supported. As you can see, they are altogether 56 56 tectonic plates. For us in Europe, of course, the most interesting one being the Eurasia tectonic plate. So let's see how the Trimble center point RTX works. So there is a three-step procedure. The first one, you have to select a coordinate system and tectonic plate. You can see the list. So the default option is the ITRF 2014. But if you click, there is a pop-up list, and you can see there is a number of coordinate systems. Of course, you have to select a tectonic plate. The default default option is auto select, which means that upon the coordinates in your file, the system will choose the best tectonic plate from the data. But if you click on the arrow, there is a list of all these 56 tectonic plates available. The second step is to select a file to upload. You just press choose file, and you select your file, observation file, being in Trimble proprietary format or in RINEX 2 or RINEX 3 format. And there is one step left. You have to provide your email address. Here I have provided mine because the results will be delivered to you via the email. Of course, you have to accept the terms of use listed in the disclaimer section and just to press process. So your observation file is uploaded in the cloud, and you can expect the results on your email. So I have uploaded observation file, and you see here, namely, this is the file I have uploaded in T02 format. And it is, so this message is saying that the file is processed, and we will send an email with the result to my email address. So some minutes after that, I received an email. This is just a copy paste, notifying me that I've received the results of processing. So there are two reports attached in XML format and in PDF format as well. So let's see what is how the PDF report looks like. So there are a lot of data. So contributors, this is my email address. So the name of the file, when I uploaded that, you can see that I did it yesterday. The start time and the end time of the file. So that means that this is a daily file for the 27th of December 2020. Observation file type is a Trimble proprietary T02. This is the observation file name. The antenna name, it's a Trimble Zephyr 3 geodetic with dome, the height, the reference to which the height was measured, the receiver name, the coordinate system. Indeed, I have chosen the ITRF 2014. Tectonic plate was automatically chosen. It was Eurasia. It was auto-detected. Tectonic plate model was the default one, Morval 56, and the processing interval was 50 seconds. There is some statistics. So in the file, since the logging rate was 15 seconds, they are altogether 5,760 epochs contained in the observation file. All those epochs were used in the processing, so the score was 100%. What satellites data were in my observation file? So there were altogether 80 satellites, being GPS, GLONASS, Galileo, and Beidou. You can see, of course, the PRN of all those satellite vehicles. And you can see that GPS is the most populated one. So about the processing results, the results are given in two reference in one reference frame, being RTRF 2014, but at two epochs, since this is a default option. The reference epoch is 2010.0, and the current epoch of data, which is 2020.99, since the data were contained in the observation file were collected at the 27th of December of 2020. The results are given in XYZ Cartesian coordinates with the precision estimate given by standard deviation, and of course XYZ are transformed or converted in latitude, longitude, and ellipsoidal height with the of course with the belonging precision estimation. Okay, so that's it about the theoretical part. So I will just recall what we went through. So yesterday I addressed the motivation instead of introduction. So what was the motivation for this webinar? How GNSS can be employed for the fast disaster response in case of earthquakes. I've addressed the global navigation satellite system. I've given an overview and the current status. Then the global, continental, and regional networks were addressed. The error sources, measuring methods were addressed as well. And of course, we have today tackled the precise point positioning PPP. What is left? There are two case studies. The first one related to kinematic assessment of Zagreb earthquake, which took place on 22nd of March 2020. And the second case study is related to Petrina earthquake that hit with the foreshock and after that with the aftershock on 28th and 29th December 2020. But in this case study, I'm going to show you how the displacements, horizontal and vertical, were detected or determined for 11 days time frame. So basically that's it. And now I'm, if there is any question, I'm opening Q&A session before we move forward on the case study. So is there any question related to topics that I have addressed this morning in the last 40 minutes? Okay, if there is no question, anyway, after, so at the end of today's webinar, there will be a specific Q&A session, which be led by Professor Bačić. So if you have any question, you can ask later on during the Q&A session. Okay, I will stop share my screen. Okay, and I'm going to open another presentation. Okay, to share the screen. I hope this is the right one. Oops, excuse me. Okay, I have run the right presentation, and now I have to share my screen. That should be the right one. Okay, I'm going in the presenting mode. Okay, can you see the screen? Can anyone confirm that the first screen is visible?
Yes, I can see.
Okay, thank you. So the first case study is related to the kinematic behavior of Kropo Zagreb station during the M5.5 earthquake, which took place or occurred on 22nd of March of the last year. And that kinematic behavior was assessed by a GNSS method. I will just quickly go through a few next slides since they've been shown or presented yesterday. So this is the map provided by European Mediterranean Seismological Center, showing that the earthquake was felt on the area within the radius of more than 400 kilometers. The epicenter was quite close to the center of the city, 8 kilometers away, and at 9 kilometers there is a Zagreb station marked with a yellow pin. This is the location where 3 faculties, namely the Faculty of Geodesy, which is my faculty, Faculty of Civil Engineering, and Faculty of Architecture. So all those 3 faculties are headquartered in the same building, marked with the location is marked with the yellow pin. Just quickly, so the earthquake created a lot of damage in the center of the city, and much affected were the older buildings. So I have to say that the newer buildings were not so much affected by the earthquake. So this is how the interior of the building of the faculty looked like in the evening of that 22nd of March. Of course, there was some damage, but the overall stability of the building was not compromised. So if we go outside, if we look at the satellite image, for example, on Google Earth, we can see that on the roof, on the southern part of the building, there is a Zagreb pin. If we look a little bit closer, we can see there is a line. There is some. There should be some shadow cast on the rooftop. And indeed, if we go outside, yes, there is a mast. Atop of this mast, there is a GNSS antenna belonging to a Zagreb station. It is a Zephyr 3 geodetic antenna. It is the same type of antenna which is supported by triple center point RTX. In addition, you can see that wire aside, it is a thunderstorm protection of the antenna and antenna mast. That station belongs to Kropos network. As I presented yesterday, it's a national GNSS permanent network of Croatia, featuring 33 stations at national territory, in addition to 80 stations from the neighboring countries, and all those stations together are included in the network solution, featuring 51 stations. So if we look closer to Zagreb station, we can see that the closest additional Kropos station is the one being in Zabok at 25 kilometers distance. This station in Zabok is 18 kilometers away from the epicenter. If we use a relative positioning method, then we need at least two stations observing simultaneously the same satellites. So I've chosen the two stations, Zagreb, of course, and Zabok, since I believed that those two stations could provide a reliable relative positioning method results. So if I have chosen another station much more distant, I will certainly lose the reliability of the results. Additional slide about these two stations. You can see on the right-hand side there is a picture of the antenna of the Zagreb over the Zabok station. You can see that the structure is much more the same. Kropos system was established in 2008, and that time it was supporting GPS and GLONASS satellite systems only. In 2 years ago, it was modernized, and in addition to GPS and GLONASS, today Kropos supports Galileo and Beidou satellite systems. So, shortly saying, all GNSSs are supported by Kropos currently today. Since relative positioning was used, and it was used static and kinematic. Data were collected at Zagreb and Zabok station on the 22nd of March, when the main shock of Zagreb earthquake occurred. Observation data included all GNSS, all GNSSs, so all four systems. 24 hours were used with 15 seconds logging interval for a static solution, and in addition, 1 hour, namely from 5 to 6 of GPS time with 1 second logging interval. So those data were used for the kinematic solution, providing 3,600 epochs. So what was obtained? This is something that we could call point cloud, featuring 3,600 solutions. Static solution is the single solution, being the most precise, the most relevant one. And if we compare the point cloud with the static solution, you can see that the majority of results are within the ±2 centimeters, which is the estimated level of precision of the PPK method. Additionally, or normally, the PPK solution should not look like this. Indeed, with the red circles are marked some results which can be regarded as outliers, but those are not outliers. Those are the signals of the earthquake. So all the processing was carried out in Trimble Business Center software, and 3D solutions were provided, namely easting and northing, given in national HRTRS 96/TM. TM stands for Transverse Mercator, which is the cartographic projection in our national system, and the height was derived in the national system, being HVRS 71. So if we plot all those data, 3,600 over time, so on the horizontal axis there are timestamps, and on the vertical axis there is a distance from each of those solution to the reference one. The reference one being static, marked with the horizontal red line. So all these distances are calculated upon this formula. And of course, we can see that approximately at the instant when the earthquake occurred, there is a spike. This spike is due to the earthquake. And if we consider the results before that time, that epoch, and after, we can see that there were no permanent displacement, meaning that there were some shaking, of course strong shaking, but no permanent displacement. What we can see that the level of bias and noise is estimated to 2 centimeters, being maximum of 25 millimeters. What about height? We can see that at the instant of earthquake, there is no specific spike. So there is no big difference in comparison to the other results. And of course, we can see that there were no permanent displacement in terms of height. So with the red line, it is represented the reference solution, and so this line shows solutions obtained for each epoch. So there are altogether 3,600 solutions provided by PPK. So if we go into details, if we want to assess that spike, what happened there? So we just have taken 1.5 minutes of data, 30 seconds before and 30 seconds after those data which were affected by the earthquake. So with the red line, we can see there in the first half of that red line, we can see a lot of shaking, and we can see the peak being 8.6 centimeters from the reference solution. Of course, here we can once again see that the level of bias and noise is below 2 centimeters. And of course, we can see that there were no permanent displacements after as a result of the earthquake shaking. If we examine the height for the same time frame, 30 seconds before and after the earthquake, we can see, of course, that there were some shaking, being maximum 13 millimeters from the reference position. But since generally the height solutions are much more noisy than the horizontal, we cannot claim that this 13 millimeters in the height are due to the earthquake. Maybe those little spikes is due to the shaking of the antenna, since you know that height is not determined independently from the position. So of course there is correlations between position and height. Of course, you have seen that there is present some level of bias and noise. As I told you, that spike could be a consequence of GNSS antenna swinging during the main shock. So if we put together easting and northing, and at just 6 seconds or 5 seconds after the source of the earthquake, the situation looked like this. So with the red triangle is marked the reference position obtained by static processing, and with blue dots are 30 seconds before the main shock was registered or felt by the Zagreb station, and with the orange dot is marked the epoch 0. So from that epoch 0, the effect of the earthquake was felt. And now I'm going to run this small video or animation showing what was going on at the time shown in the upper part of the image. So this animation is twice accelerated, so it is speeded up, and you can see that after approximately 13 seconds that the shaking was attenuating. So the majority inhabitants of Zagreb city would tell you that the shaking lasted for 13 seconds. Of course, it depends from where those citizens come from. If they are closer to the epicenter, the shaking lasted longer, and of course it was stronger. So at 5 o'clock 25 minutes and 7 seconds according to UTC, the situation looked like this at Zagreb station. So in addition to the blue dots, orange dots, we have green dots. So green and blue dots belong to those time windows before and after the main shock. If we remove the effects of the earthquake, then we have only blue and green and gray dots, and you can see that all those 60 dots are within a range 13 millimeters in direction east-west, and 8 millimeters in direction north-south. And if we consider only those positions affected by the earthquake, we can see that they are in the range of 13 centimeters in the direction north-south and almost 6 centimeters in direction east-west. So it was a pretty strong shaking. You have seen the damage that it caused on our building, in the halls of the building, and even on the wall in my room, which I'm looking at right now. Additionally, what we have estimated or concluded from those effects of the earthquake. So if we consider the distance between the epicenter and the receiver, if we consider the estimated depth of the hypocenter provided by the Croatian seismological survey, we can calculate quite easily the distance between the hypocenter and the receiver, being 12.5 kilometers. And if we divide that distance by the time elapsed since the origin of the earthquake and the time it was felt by the station, we can derive quite easily an average speed of the seismic waves, being estimated to 2.1 kilometers per second. This is something that you should have seen yesterday, or something like this. This is the interferogram which was derived from Sentinel-1 data from two passes of the satellite-1 satellite. The first one took place before the earthquake at 17th of March 2020, and the second one on 23rd of March 2020. And from those two passes of Sentinel-1 satellite, this interferogram was derived. What we have on this figure, we have with these two dots in the center of the figure, we have the location of the main shock, and which was estimated to magnitude 5.3, and the smaller dot represents the foreshock, which was weaker, of course, estimated to magnitude 4.8. With different colors, with the color range from blue to red, are shown the displacements. And if we just estimate the rough position of Zagreb station, which is somewhere here, and if we estimate the displacement, we can see that actually there were no displacements. So the results derived by GNSS and results derived by INSAR those two results match pretty a lot. So this, I have to say that this interferogram was compiled or produced by my colleague Marin Govorchin, coming from the same faculty of geodesy of the University of Zagreb. Just few explanations. With the blue, with the white line are marked the faults, which are, let's say, guilty for the earthquakes that have occurred on the Medvednica epicentral area. Now I have a small additional animation. It is animation which was provided by colleagues from the Faculty of Science, Department of Geophysics. And this video, this animation, basically shows the how the earthquake waves was behaving on that 22nd of March 2020. Okay, I am going to run this. It is posted on Twitter profile of Marin Gorchin. And you can see this is the so this picture, let's say this is as it is seen from the southeast direction. So basically you can see how this earthquake waves was moving at that day. Okay, I'm going back to my presentation, and basically this is my last slide. Okay, this is the end of the first case study related to kinematic effects of the earthquake assessed by GNSS relative kinematic relative GNSS method. Is there any question related to this case study? I cannot see any. Okay. There is a question about yes. Can you speak, please? Can you unmute yourself?
Thank you. I'm Mohammed Mahmoud Sbeb from Morocco.
Okay.
I'm just have a question about choosing the position from to extract the information about the IGS, because in your cases you have a station in your university, but in my country, for example, in Agadir, we have a problem with the earthquake, but we don't have, like you, a station to calculate and estimate the same thing that you have done in your case. Thank you.
Yeah, of course. I understand quite well your question. So you must have such a network. You must have a receiver. So whether this receiver is coming from a network or it is installed by yourself, that is, you need that. This is something essential. In Croatia, we have our national permanent GNSS network, and all countries in Europe have such or even few networks. IGS, you know, so independently of being your station coming from the national or global network, it has to be close to the epicenter in order to be felt. So if I, for example, if I were using some station, let's say from Italy, I would not obtain any results relating to the earthquake in Zagreb. So if the station Zagreb were much more away, not at 9 kilometers, but let's say at 100 kilometers away from the epicenter, I would not obtain any results. So the answer is you must have such a station. You must have such a station in order to assess the effects. I will show you in the after the break, obviously, in the second case study. We have used another method, but we have used still the station from Kropos network, and of course we have used the closest one to the epicenter, since we estimate that those station was the most one affected by the earthquake. Okay, are you satisfied with the answer?
Yes, yes, thank you so much.
But tell me, just I have one question for you. What about GNSS network in Morocco, in your country? Do you have any?
For now, we have two satellites that named Mohammed 6. Just they have a 2 year of years old. It's very recent. So we have we are in the right road to have the same thing that you have, inshallah.
Okay, so I wish you good luck in establishing a network there.
And so sorry for my my English, because my formation is French, then English.
Okay, I see. Yes, and you can obviously you can see the benefits of such a GNSS network.
Yes,
just bear in mind that assessment of earthquake effect is just the only one benefit. There are many more benefits of such a network, and this is the reason why all countries across Europe have established such networks. Even a private companies have established a number of such networks. Okay.
Yes. Thank you so much.
You're welcome. Is there any question from anyone else? Okay, if not, I would make a break of 15 minutes and we will be back at 10:30. Okay, so take a breath, take a coffee, and we will be back in 15 minutes. Bye. Hello, we are back again. It's 10:30. It's time to resume. It's time to go on. Okay, I'm going into full screen mode. Yeah. Okay. Can anyone confirm? Can anyone confirm me that?
Yes.
Yes, it's visible. Okay, thank you, Professor.
It's
So
okay, yeah.
Okay, thank you. So this is our second case study, and it's related to displacement of Kropos CISA, which is abbreviation for the CISAC station, in the period from 27th of December, last year, 2020, to the 6th of January this year, assessed by GNSS PPP method. So just to recall what was presented yesterday. So this is a map provided by European Mediterranean Seismological Center, showing the area where the earthquake which took place near Petrinja in Banja region was felt. And indeed, it can be seen that it was much stronger than the previous shown one. It was felt at a distance more than 600 kilometers away from the epicenter. In the table on the right-hand side, there are the very basic data about the earthquake. So the location of the epicenter given in ellipsoidal coordinates being latitude and longitude, estimated depth, the moment magnitude estimated to 6.4. It is 1 magnitude stronger than those occurred in Zagreb, and the time of origin was 29th of December 2020. Indeed, a day before occurred a very strong earthquake, and we all thought it was the main shock, but in fact, it was a foreshock. The big one, the main shock, occurred a day after. So just to look at the location, so this is the estimated location of epicenter. It is southwest of the town of Petrinja, 6 kilometers away from the center of the town, and at the same time is 13 kilometers away from Glina town, and the biggest town in that area, which is Sisak, at 15 kilometers away from its center. In Sisak, marked with the yellow pin, there is located Kropos course station. If we look at the peak ground acceleration map provided by USGS, we can see that the peak acceleration was quite strong, being even higher than 50% of G, and strong PGA caused strong shaking, and strong shaking caused damage. And if we look just how the center of Petrinja town looked like soon after the main shock, you can see a lot of buildings fully damaged. So the roof construction completely collapsed, damaged or ruined some vehicles parked on the streets. This is another picture showing the the material damage. This is once again center of Petrinja, but of course you can see material damage. There were bigger damage, much more important damage that hurts much more. There were 7 human casualties as well. So once again, this is Kropos network. There is a station SISA in Sisak, 15 kilometers away from the estimated location of epicenter, marked with this dots or concentric circles. So the data that were used for the assessment of earthquake, data were collected at SISA station. They were downloaded from GPPS service of Kropos in the Trimble T01 proprietary format, and the logging interval was 15 seconds. There is a time frame featuring 11 days from 27th of December till 6th of January this year. On the figure in the center, you can see the map of Kropos network. By each green pin is marked each single station. Okay, the results was processed by Trimble Centerpoint RTX post-processing service. I've talked about it earlier this morning. So basically what is needed, I showed you that there are 3 steps needed in order to obtain the results. First of all, you have to select the coordinate system and the tectonic plate. The default options are ITRF 2014 and auto selection of tectonic plate. Of course, for us, Eurasia tectonic plate applies. The second step is to select a file. I've chosen daily files downloaded from GPPS service of Kropos in T02 format, and I've uploaded all those files one at a time. So that means that I've run this service 11 times. In fact, 10 times, but I will show you soon after why there is 1 day of data missing. And the third step is to provide your email address, since the results will be delivered on that email address. Before you proceed, you have to confirm or accept the terms of use. And finally, you have to press the button, yellow button process, and the processing is initialized. Of course, as I told you, I have uploaded 10 files, not 11. Why not 11? Because on the 30th of December, the station was out of service, so it hasn't provided enough data. And indeed, as you can see in this red box, it says that the order does not meet the session length requirement. the service only processes orders that are between 10 minutes and 7 hours in session length. So indeed, there were just few epochs, not enough for being processed. So all those green are notification of acceptance of the data uploaded or files uploaded. As I showed you earlier this morning, I have received the results by email. The results are given in XML and PDF format report. What is in report I have already explained. Since there are coordinates given in RTRF in 2 different epochs, the current epoch being 2020.99 and the fixed epoch 2010.9, I have selected this fixed epoch for my coordinates. And of course, there are rectangular Cartesian coordinates x, y, z, and the ellipsoidal coordinates given in terms of latitude, longitude, and ellipsoidal height. I've chosen x, y, z, and what I did for the sake of visualization, I transformed those coordinates in plane coordinates, easting, northing, and heights, referred to GRS 80 ellipsoid. So basically, this is the schema of general schema of transformation. I just applied this direction. So from X, Y, Z, there is a transformation or conversion to phi, lambda, and h, and finally ellipsoidal coordinates are transformed into plane coordinates in transverse Mercator projection. So those are the results obtained by center point RTX or PPP method. We here have 11 daily solutions, but not 11, we have 10, since you have seen that one file could not be processed because there were just few, not enough data for processing. So this is the start. This is the 27th of December 2020. So this is a day before the earthquake. Then the day after, this is the solution. There is no significant displacement on the day where the foreshock occurred. Then we have the day of the main shock, and we can see that in between there is some displacement. Just bear in mind that this grid has a step of 1 centimeter. So this is 1 centimeter, this is 1 centimeter. So we can here estimate that there is, let's say, 12 or 13 millimeters, something like this. Then we do not have data on the 30th of December. So I suppose that the result should be somewhere here. And then we have daily solutions from 31st of December till the 6th of January. And we can see that all those solutions are grouped here. So from the beginning of the time frame to the end of the time frame, we have a displacement of 5.2 centimeters. So that was something expected, since the earthquake was very strong, and the station is 15 kilometers away from the epicenter. We have also results obtained by static relative positioning, and we can see that the results, the displacement, are much more the same. So I'm going back to show you the results obtained by PPP method and the results obtained by static relative positioning. And you can see that there is a negligible difference in estimated horizontal displacement. So those results are obtained by quite different methods. There is a lot of differences. There are a lot of differences, but the results are almost the same. And this is the proof that both methods are very reliable in assessment of horizontal displacement in this case. What about height? So those are the results of daily solutions obtained by PPP. You can see there is a gap. So there are daily solutions. There is a gap on 30th of December. And if we consider the height obtained for the day before the main shock, before any shaking, being the 27th of December, and so if you consider the, let's say, initial date and the final, we can see that there is a subsidence estimated to 3.4 centimeters. If we consider the results obtained by static relative positioning, and so there is, I have to say that there is a much longer time frame considered, but if we just consider this time frame from 27th of December to the 6th of January, we can see that there is a subsidence of 2.1 centimeters. So going back to solution provided by PPP and forward to solution provided by static relative positioning, we can see that there is a bigger difference than in horizontal displacement, but this is quite expected since we have to be aware that the heights are determined by worse precision in comparison to horizontal positions. But nevertheless, bearing in mind all the differences between methods, the results match pretty well. We have also examined the availability of observations contained in the daily files, and you can see that on the 30th of December, we had almost no data, and because of that, we have no solution. You see that on the 29th of December, where the main shock occurred, we have data, but not full data. And of course, later on 31st of December, 1st of January, 2nd of January, we have also some data missing. And from 3rd of January on, there we have full data. So this is proof that the station itself has suffered from this earthquake, mainly due to power issues. And now, as I did in the first case study, I'm going to correlate, let's say, those results with results obtained by INSAR. Similarly to Zagreb, there were 2 tracks of Sentinel-1 satellite. This image was produced, this interferogram, by INSAR method. And if we estimate so the displacement on the location of CSAC with which should be somewhere yellow or reddish, we can estimate the displacement of, let's say, 2 centimeters and a half, approximately 2 centimeters, and so on. What is displayed on this figure? They are displayed the epicenters, and of course there is displayed another epicenter, very interesting one, and I would say very important one, which took place down in 1905. And by assessing the effect of that earthquake, Andrija Mohorovičić discovered discontinuity, which was, of course, named after him, and now it is well known as Moho discontinuity. Okay, there is also with the red line is marked the Pokupsko fault. It is the fault which is, let's say, guilty for those earthquakes that occurred in this area. As you can see, there is a lot of points, smaller one marking the weaker number of weaker aftershocks that took place there. Once again, this interferogram was provided by my colleague from the Faculty of Geodesy, Marin Gorchin, and you can access this image on the link given at the bottom of your screen. I have a small animation of this, of the main shock occurred. I'm going to run this, hopefully it will work. Just a minute. Yes. I hope you can see this. So basically, this is the animation of the waves caused by the earthquake. If you concentrate on the area of Zagreb, you can see that Zagreb was also affected heavily by this earthquake. So it was a stronger earthquake. It lasted much more than the Zagreb earthquake. So even at 50 seconds elapsed since the beginning, you can see there are some small effects still visible. Okay, and just to say, this is the velocity of the Z component, being in red being positive and in blue being negative, means when it is positive that the left.
Dear Daniel, we do not see anything.
Okay, I'm going back. Okay, have you seen this video or not? If you haven't seen it, you can access it through this link, which is given on the bottom of the screen. And actually, that was my last slide. It's almost 11 o'clock. So I will open Q&A session. Is there any question related to this case study?
Okay, thank you, Daniel. Hello, everybody. So we are approaching our last session. and I will share my screen. Just a second, please. Can you see my slides? Before I
Yes.
start,
Yes, we can
thank you.
see.
Before I start the presentation, a few technical information. So we are kindly asking you to fill the evaluation form, which Vesna is now, the link to evaluation form of Vesna is now loading in the chat. So it's a 2-3 minutes evaluation form, and it will help us to evaluate the quality and relevance of the webinar and help us to improve ourselves next time. So this is number one. The second information which I want to share with you is that the links to recordings of the webinar will be made available today. So you will receive mail or it will include those links, and it will include link to evaluation form if somebody will do it later. Also, all participants who participated most of the time, or all the time, all 3 days on the webinar will receive the certificates of attendance, and they will be sent to you via email in coming days. And before we start our last session, I will stop sharing my screen and kindly ask you to turn on your cameras so that we can make a group photo. We have a very serious project manager, and we have a document, joking a little bit, that we have conducted the webinar. So I will stop sharing my screen. So pictures are coming. Glad about this.
We'll say cheese.
Wait a second, few more seconds. So good. Yeah, okay. I am aware this is a frequent problem that sometimes cameras are not working proper, or they are not available, and so on. So Vesna, you can hit the photo.
Yes, just smile, please.
Good. Okay. Okay, Vesna?
Okay, yes.
Good.
Thank you.
Thank you very much. And I will now continue sharing my screen and go in this last presentation. So here I have stopped, and I will focus on 3 aspects. It's about the quality and the consequences of such researches or usage of technologies which we have presented in case of catastrophic earthquakes. The second, I will turn attention to the risks which appear when we compute make such computations under condition that we are trying to deliver fast response, and also give some conclusions. Raquel, you want to ask something, please? No, wait a second. No? Okay, then I will continue. Okay, so, and let me start. So, the content is the quality assurance in computation and interpretation process and information dissemination activities. I will not go directly in the quality assurance of specific method. This has been addressed by both Marian and Daniel, but I will turn your attention to certain aspects of the quality assurance and issues which appear when we are trying to give a fast answer. And another issue is also what are the consequences when we disseminate those results. Then, what are the consequences if surface displacements appears, and what are the necessary actions? What are the risks being, so to say, affirmative and doing such computations and publications in case of catastrophic earthquakes, and summarize it in conclusions. According to presentations which have been given, we have in fact two situations. We can provide the support to rescue and recovery activities and in general to overall general populations in two manners. So we can be the facilitator of exchange of information, so to establish applications, and in principle, we are not responsible in this case for the content of information. Or we can be a creator of information, so author, and then it's our full responsibility for the content of information. And in these two situations, there are also different responsibilities. The problem would not exist if we are, so to say, following the classical approach, scientific or professional approach, that we make computations and test those computations in, so to say, normal or complete full procedure, including all factors, making all necessary checks, independent controls, etc., etc., as one scientific research or professional work should be done. But in the case of the disasters, we don't have this possibility because we want to deliver those informations fast, this information fast. So basically, the need or intention to present to public as soon as possible the information of scientific or of computations, results, consequences of a catastrophic earthquake is at odds with the need to carry out the processing of Earth observation and GNSS data with incomplete scientific and professional rigor. So taking in account all factors and conducting all controls which will guarantee the correctness of the result. So what does it mean? If we are a facilitator of exchange, information exchange, so if we have developed application and we are maybe also administrator of this application, in principle, we are not responsible for the content of information which will be published on such application, because they are basically more or less offering free access to the citizens. Our responsibility, however, is that for the functionality of the application, so how the application will work, and also for administering the application. We could add here that also responsibility in the part of the administering application responsibility is also to check to the certain level content which is loaded by the citizens or whomever on the applications, that those informations are, so to say, in line with the purpose of application. So I'm not speaking about any kind of censorships or something like this. I'm simply speaking about maybe some automatical filters which will, so to say, remove or at least slow down publication of the content which has no real relation with the purpose of the application. And we presented two applications to you. One which is generally open to everybody, the Auton, and the second one which was rather closed, so only for use of at least considering loading the information to the registered users. So the emphasis of both types of applications is on functionality, on simplicity, and on graphical quality, because in principle, first what we, so to say, see or what is communicated to us are graphical informations, and then deeper clicking on one of those red buttons, or we can access also alphanumerical information. It's a little bit different when we are creators of or authors of information, so creator and publisher of information. So in principle, we cannot be responsible for the usage of information which we have published, but we are in a way indirectly responsible, because the way how our information will be used may also depend very much on how we have presented this information. And in this sense, we are responsible very much for how the information is presented, and of course for content of information. And we have demonstrated several services or several results in the yesterday and today, which are providing information which is relevant to the rescue and recovery services or some other services, or are interesting for the citizens. So in this sense, those informations are then used or might be used for certain actions. So let us see a little bit how and what can be, what is the responsibility. So emphasis when we are author of information which will be published is definitely on reliability of computed and published results or information as such. So the information which we deliver should be reliable. Also the conclusions which we are drawing from computed results should be very cautious. Very cautious. What does it mean, very cautious? They should simply limit themselves really on the content which is really proved by the results which we have achieved in our computations. Then, when we are authors, it's very important how we will communicate the information to the public. We can make it spectacular, or with breaking news, or something like this. I don't know. European continent is sinking. We know all because of the climate change. And then in the 15th sentence of some article, there is said that this sinking will happen in 500 years or something, or 5 million years. So, I mean, it's not, especially in the cases of catastrophes, where people are extremely sensitive. We have to be very cautious how we will present the information. And finally, there should be a transparency of the process of computation. So unfortunately, we are facing today that some results or some statements are made, and it happens that there is no argumentation how these results have been achieved, or what is the process behind some statement, and how we have come to this conclusion. To make it more clear, I used those examples which we have presented. And for example, first are those two services from European Mediterranean Seismological Center, where we have a picture of earthquakes which are happening on a daily basis, and also a picture of a specific earthquake, and the seismic map of this event. And what we know, this is a standardized service. So it's a service which has been built, established. It is connected with great number of institutions which are responsible for seismology worldwide. And it is the whole process is highly automized, and we see also that the first results when earthquake happens, and then after a few hours or in day or two, the final result about the epicenter, hypocenter, and magnitude of the earthquake differ usually insignificantly, so maybe 0.1 or 0.2 on Richter scale, what is in a case of strong earthquakes of magnitude 5 or more, not essential. So this service has been established exactly for the purpose which we are speaking about, providing a fast and reliable information, and this service is doing this. But there is a, so to say, infrastructure behind this, which is also enabling that this is really so. When we speak about radars and INSAR, if we want to deliver first result or very fast result in the computations, we may not take in consideration all necessary factors. For example, atmospheric corrections, influence of ionosphere and troposphere, etc., on the signal propagation. have an impact on the final result. And if we are trying to do it in a day or two after the earthquake, then it might be that you didn't, or somebody X did not, simply was not enough time to calculate in all necessary factors. So, for example, in the case of Petrinja earthquake, there were several independent computations using radars, satellite radars, and we could see that those results somewhat differ between them. So the differences were not extreme, but I would say also that they were not fully insignificant. So in this sense, there is then a space for, definitely a space for further thorough computation and publication of reliable, correct data. So in this sense, the scientific caution is necessary, and especially in interpretation of the results, because we should be aware, or we should at least say that some level of to make a remark on the reliability and level of accuracy of received results. Just saying, for example, that interferogram is showing, I don't know, 10, 20, 50 centimeters shift in the center is simply incomplete information. Similar is with the computation of dynamic so kinematic surface displacement during the earthquake. So if you want to do it, all those computations require time. So you are trying to compute a relatively big amount of the data, because you want to have a picture before the earthquake and after the earthquake. And you have a lot of reference stations. You are using 1 second, 1 hertz registration rate, or even higher if you have such receivers. So basically, you have to make some assumptions. And for example, a first assumption is that a neighboring course station is not affected by the surface displacement during the earthquake. This some 29, 30 kilometers, like in case of Zagreb, and assumption has been made. So this might be true, but this also might not be true. So therefore, as Daniel, I think, also mentioned, after the earthquake, we made a lot of computation to check the behavior of the course stations which surrounded Zagreb course station, with, so to say, a third line of stations which are 100 kilometers away from Zagreb, which were definitely not affected by the earthquake in a sense of the surface displacement. So these are some risks, and another risk is also, or another information which we are aware of, it is the question, where is the antenna, or how is the antenna of course station stabilized? So for example, as Daniel showed, our antenna is on the roof of the 5 floors high building. So the presented result is a combination of surface displacement, but also a building shaking. And this is especially, I would say, visible in this movement where building went first in the direction of south and then shaked back to the north. So this is definitely a result not only of the surface displacement, but also a building shaking. So also presenting such results, we have to be cautious and should you say, turn attention of the readers of those aspects. Similar thing is when we speak about permanent surface displacement, like in a case of course station CSAC after the Petrina earthquake. In those computations, first of all, we have to follow prescribed procedures. So we, in the rush, we may, so to say, neglect the fact that we are not using precise orbits and things like this, but we have to follow prescribed procedures in computations to be sure that in this aspect we made correct computations. So also the question is, the assumption is that neighboring core stations are not affected with the surface displacement. So this is the same issue like with the previous station. But also in both cases here, so in kinematic surface displacement and in static or permanent surface displacement, we should be aware that GNSS technology has a certain level of measurement noise. So we cannot interpret anything what is on the level of measurement noise or near to the measurement noise and to make positive conclusions from such results. We have to have clear signals. And for example, in this case, we have really a clear signal. 7 day computations showed either in relative static or in PPP. With PPP method, we received more or less identical results. So showing us that there was a shift, the surface displacement in the southeast direction after these earthquakes on 28th and especially 29th of December. So again, we should be cautious when we interpret the results we have achieved. Why should we be very cautious? So, first of all, today, many countries, or I would dare to say even most countries, changed their national reference systems and frames, and they rely on GNSS measurements. Standard-wise, at least in Europe, I can say with confidence, the national reference frames rely on permanent GNSS networks, like in Croatia, on the Kropos network. And in this case, today, GNSS coordinates of course stations are global and absolute, so they are fixed and not so any surface movement, geodynamical or such accidental, when earthquake happens, are basically resulting in the change of the coordinates of those course stations. So it is not like in the, under quote mark, old times when we had our local reference systems, which were more or less moving with the surface because they were defined based on the fixed points on the Earth's surface. This is today not the case. We have a system in space which is not affected by the surface movements of the Earth. So if surface displacement occurs caused by earthquake, this will cause shift of the course station. It means that the coordinates of affected course stations or station will change. And in this context, such a station, affected station, may not be used in this case until their coordinates are not recomputed. Why? Well, very simple. We are today in practice mainly using, if we want to achieve high accuracies of a few centimeters, we are using kinematic in real time. So basically, VPPS services of the permanent GNSS networks. And in this case, if we are computing, we are measuring near this affected reference station, we will basically receive wrong coordinates for the virtual reference stations. So our results of measurements will be wrong. Not only the reference station, we have additional problem, and this is that all points of stabilized points of the geodetic network or geodetic points, if they are in a region which is affected by surface displacement, are also affected. So their coordinates also changed. And since, as I said, we rely on GNSS technology, we have to also ultimately have correct coordinates for all those points. So we have to remeasure the points of a geodetic network to be able to use those points and also course station in future. So to show you an example, in January this year, after the earthquakes in Petrinja, State Geodetic Administration, so Croatian National Mapping and Catastrophe Authority, made a fast resurvey. So it took one or two, so few days, and the points of the geodetic network in Sisak, Petrinja, and town of Glina, who is left outside of this picture, have been remeasured by the RTK, so a real-time kinematic method, where before this, just a few days after the earthquake, when it becomes clear that there was a surface displacement, the Sisak course station was taken out of the network, so out of the computation of VRS solutions, so for the purpose of kinematic real-time measurements. So you can see that the computed displacements are quite high, so even over 3, 4, 5 decimeters. So in the Petrinja network, so around the town of Petrinja, much lower in the Sisak area, which is also showing us very well the intensity and spreading of the earthquake. Of course, you can also see some strange indications like this point in left bottom, which has a complete opposite direction of the shift, which might be possible, but we have to so to say also be cautious with such interpretations or such results, because first it is very important how the computation or survey and then computation has been done. So this was only one session according to my knowledge, so each point was occupied once, so there is no control about the occupation and all errors which can appear during the measurements. We have also no information we have no information if there was some displacements or errors or shifts of the point in time from the date when they were measured till so initially measured till the earthquake time. And in this sense, we have to assume that outliers or some errors are also possible. And also we should be aware of this. So in this case of such measurements, the scientific cautiousness and also transparency about the work, how it has been done and how it has been computed, is very relevant for the understanding what this picture or those results present. Of course, also in SGA, they are aware of this. So basically, this was just a first result to give us indication what has happened in the region. And after this, basically a project has been launched to resurvey properly all the points in the region and to correct the coordinates of them. Going back a little bit to a Sisak coarse permanent station, you can see on the picture that Sisak is surrounded by the river Kupa and Sava. Here is Sava, here is Kupa river, and you can see that both rivers are meandering, so they are not going in line. So it's a very flat area and it's a flooding area. And you heard, Daniel, that computations have shown that coarse station in Sisak sinked for 2 or 3 centimeters, dependent on the computation method. And this is an issue, or it might be an issue for this area, because it could mean that also the dams of the rivers have sinked, and it might have some repercussions in the future. So, and this is what I wanted to emphasize, that our results may have consequences later when the recovery is take place, and So when we publish the results, the information, we have to be aware that, especially in the situation of, in general, this is so today, but in the case of catastrophes, media incline to bombastic headlines, so to bombastic news. We think that it is a responsibility of scientists and professionals that the information is presented in a proper way. Proper means that whatever result is, we should also say, or communicate the limitations of this result. So if we are aware that this is something what we can say a preliminary result, then this has to be communicated, or what is the level of accuracy or level of reliability of this result, etc. So we should be very cautious in our statements. I'm not saying that we should not release the informations of our computations, but we should really take thoroughly how we will do it. Even knowing that after 3 days, news is forgotten, as you know, this is so sad. So when we publish information, we should really think good how we will do it, towards whom we will do it. The information may be published generally to everybody. It can be published to certain rescue service teams or organizations, to the responsible governmental authority, internally among the professionals or scientific society. So there are levels, various levels on which we can, in which groups in which we can disseminate our information. Further, why? Because there are risks. If our information by some reason is unreliable or incorrect, it can, first of all, mislead rescue and recovery services or efforts. And this is definitely not something what we would like that happens. It can cost the time, and the time is always lacking in a rescue and recovery activities, especially in the first day after the earthquake happened. Even worse, our information may create a confusion. And this is definitely not something what is necessary or what anybody wants in the case of the catastrophe. And it could cause unnecessary costs to the society. So basically, if there was some sinking of the surface, so at least what should be done, so to say, the situation with the level of, or the height of the dams, river dams, should be checked and controlled, because if on some location surface has sinked on then downwards not, it could be a reason for some additional works to ensure protection from flooding, for example. Then internally, it can cause, if we are, so to say, providing unreliable and incorrect information, it can create a loss of credibility for specific profession, institution, company, scientists, professionals. So to exaggerate it a little bit, the European Football Championship just finished, and you could see the reaction of the media and people when some referee was not good on some game, and basically, yeah, the XY was named, but immediately people were criticizing all referees or VAR or whatever. So this is so also with in this case. So one or two errors or unreliable, incorrect information may bring shadow over a group of people or institutions, what nobody, I think, would like that it happens. So we should be aware of those risks, and being aware of them, basically we should take all necessary, all possible measures to ensure that our fast received results are reliable and correct. And we should also be very cautious when communicating this to the society. So having this in mind, I put few conclusions together. So I think from the given presentations, it's quite clear that satellite technologies like INSAR, so radar, and GNSS are really mighty tools which, in case of catastrophic earthquakes, can provide valuable information to rescue and recovery services and general public. I just read it in one scientific newsletter this morning that a group of scientists from Germany have developed new algorithms for computation of radar signals measurements, which are increasing the accuracy of the interpretation of the results, and also they developed new algorithms which enable much faster computation. So things are progressing, and those technologies will be even more and more powerful soon. So in this sense, really, they should be used in the case of natural catastrophes like strong earthquakes are, as support to rescue and recovery services and general public. So they can really provide reliable information about surface displacement in cases of catastrophic earthquakes. What is the catastrophic earthquake? It's hard to say. I mean, based on our experience, what we dealt recently, I would dare to say, to give a rough estimation that these are the earthquakes of magnitude above 5.0 on Richter scale. But we are also aware that there are also stronger earthquakes which are not resulting in surface displacement, and there could be also weaker earthquakes which result in surface displacement. So this is really a very rough indication, nothing more. So in case of something what we will call catastrophic earthquakes, a fast check if there's been a surface displacement should become a standard activity of a network GNSS network administrator and scientists. So this, in our opinion, really is not, shouldn't anymore be a case of, well, I'm interested to find out, was there any surface displacement? No, this should be a standard activity in case of such event. And this is especially important for course stations which are near the epicenter of the earthquake. Again, I must say, it sounds bad. It's each earthquake, a catastrophic earthquake, is something what is really terrible. But considering science, it's opportunity, and in this sense, for example, considering Zagreb and Sisak earthquakes, we got the opportunity to make these researches due to the fact that core stations were very near to the epicenter. So I don't want to use word lucky in sense of this, because this is really a wrong word, but simply it gave us opportunity to make those computations. So detected surface displacements on core stations or stations should then result definitely with its temporary exclusion from the network. So a decision has to be done very fast, because in case of catastrophes, also engagement of the devices, GNSS devices for rescue and recovery activities is very intensive. So we don't want to create a situation in which permanent GNSS network will deliver wrong results. And finally, regardless to the technology and the computation and measurements, if done, they must be conducted in accordance to the prescribed procedures. So this is really the only safe way to achieve reliable results. You cannot, so to say, jump over the steps or avoid some controls or influences just to give results, get results immediately. Just to go back to this picture. So, for example, it took some 8-9 days before this computation was finished. So before we were confident that the result which we achieved is reliable. So now imagine that we have computed only 27th, 28th, 29th, and 30th of December, and we would get big discrepancies. We would have only 3 days, and we should rely on the result of the 30th of December. Luckily, in this case, the result would be okay, but we would have no guarantee that this is really so. So in this sense, we have to be cautious, and we have to ensure that we have sufficient independent results which are guaranteeing or independent computations which are guaranteeing reliable results. And finally, when presenting or publishing results and informations, authors must retain scientific cautiousness. So we have to be aware that results which we are publishing may have consequences which in a case of unreliability of our unreliability of our results may cause really harm or problems to rescue services or to citizens alone. So with this 3 pages of conclusions, basically I would like to finish here. What we are further working, just for your information, is basically a combination of different technologies. So basically, our further research in a moment is also focused on a combination of data from seismological data and GNSS data, and combining all those data with the radar data results, so to get a more comprehensive interpretation and even more reliable interpretation of the event which we faced in past. And regarding this training and other trainings, this training is part of EO4GEO project training. So on the EO4GEO web page, there is a directory, or there is a column resources, and in it there is a body of knowledge. So the training as such is resulting from existing concepts which are described in EO4GEO body of knowledge, or book, how we are calling it, and also the training materials of previous and future trainings are also are or will there be made available as the training materials of this training. The trainings are continuing, and you can find announcements of next trainings on EO4GEO webpage. And if you are interested in EO4GEO activities, there are several opportunities to join. So you can also, I'm inviting you to go to the project webpage and look into the informations which are provided there. We got also yesterday one question about is there a possibility to translate the materials in the presentations which we delivered here in other languages, concretely in French. Well, I don't know, will we be able to do this? This is a lot of work. There are a lot of slides, etc. And we are not so good in French, so we have to use Google Translate or something like this. So I'm not sure that we will be able to do this, but anybody can use Google Translate and translate it in very many languages globally. So this was the last presentation. Here is also the web page of EO4GEO project, also mine, and you are free to contact either me or Marian, Daniel, or Vesna if you have any question. And now I will stop share the screen, and if there is any question or comment, please, floor is yours. I have here. Marian put his answer on yesterday's question on the chat, and I can also give you just a second the link on this newsletter where the result, this information about so to say, modernization of algorithm on radar computation, INSAR computation, or is given. I'm trying to find it in a moment. I'm not seeing it. No. 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 Cannot find it in a moment. Any comment, question from your side? Please, Vesna also put the link to the evaluation form, so you can fill it right now and make us happy so that we can make an evaluation. And we have emails from you, from your registrations, so the links will be sent to you. Mohammed, please.
Sorry, I have just a question about the evaluation of the training. In the last section, if there is a question 34, would you like to receive a certificate participation? But you say that please provide your email and your name. But there is just one place to make an email or a name for the certificate.
Just a second, I will enter it now fast. I have question 34. Yeah, okay. Sorry, I have to click on all questions to come to this question.
It's the last question.
Yeah.
34, 35. 35, if yes, please provide your email and as well as your first name and last name, but there is just one place. If we must make our email and name at first, or the same thing. I don't know.
I'm now a little bit confused. I'm a little bit confused, Mohammed, because I went through the questionnaire and the questionnaire has 28 questions.
Okay, sorry.
I don't know where did you find those other questions. So it's stopping on question 28. Please click on this this link which Vesna has provided, and we will send it again. I will check it, but I'm not coming above questions. There are 28 questions.
Željko?
Yes.
For certifikat otvara se 34. Znači neka upiše ime, prezime i email.
So, okay. Write in your email on which you want to receive the certificate and also your full name. Okay, in the same line.
Okay, thank you.
Thank you, Mohammed. Anybody else? If no, it's exactly 1 minute till noon here in Zagreb. And I want to thank everybody for participating in this webinar. I hope it was worth something to you, and we will continue with those activities, the EO4GEO project in general, but also us, the faculty of Geodesy, University of Zagreb. And if you have any question or interest or about what we have presented, you can contact us anytime. Thank you very much. Enjoy the day, and we will meet us next time. Thank you and bye-bye.
Thank you. Goodbye.
Bye.
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 Thank you. Bye.
Bye.
She said, where you wanna go?
Papi, I have replied on your question if you are still here. No, he went. Okay. Okay.
Galaxy also asked.
Yes, I saw it. Well, yes, the answer is yes. I mean, the potential of when we have spatial information, spatial data results as we receive them from the GNSS and from INSAR, and then all those activities which I mentioned, there is a lot of space to combine different GIS applications or possibilities together with the achieved results. I mean, for example, there are cases in a moment the GIS is used after the earthquake in Sisak, some 3,000 because so many buildings, houses have been demolished. 3,000 containers have been distributed to the people so that they can live because their houses are not for living. So basically also a GIS was established where all those containers are registered, and a system has been, so to say, with information filled, etc., etc. So that there are plenty of possibilities, plenty. But it depends always on specific, on the purpose and the need and the specific situation which some earthquake has created. Yeah. Okay. You're welcome. So with this, I will also leave the meeting. Thank you and bye-bye.